Yes, I told already. This also DC to DC converter. If the DC to DC converters are used for low power application, then it is called SMPS. If SMPS is nothing but a DC to DC converter used for low power application. Low power application. If the DC to DC converters are used for low power application, then it is nothing but a switched mode converter. Mainly, this SMPS are broadly classified into two types. This SMPS converters are broadly classified into two types. One is hard switching converter. Hard switching converter. Hard switching converter. Another one is soft switching converter. Yes. Soft switching converter. Okay. In hard switching converter, again without isolation, we can use the converter without isolation, then with isolation. In with isolation, again the converters with unidirectional excitation. Unidirectional excitation. And we also use the converter with bidirectional excitation. Okay. Bidirectional excitation. Use the converters with bidirectional. Without isolation, the examples for SMPS converters is that you already studied this, already explained. Buck converter, boost converter, buck boost converter, Chook regulator. Okay, these are the examples. With unidirectional excitation is for flyback converter, another one is forward converter. With isolation, the example of bidirectional excitation is push-pull converter. Yes, push-pull converter, half bridge converter, another one is a full bridge converter. Full bridge converter. The examples of soft switching converters is hard switching and soft switching. That is, soft switching is resonant converter. Resonant converter. Resonant converters are soft switching. In soft switching, again, two types of switchings are there: ZVS switching and ZCS switching. Zero voltage switching and zero current switching. Okay, these are the different types of SMPS circuits we are using. This I already explained. But you concentrate. I want to give one or two examples with isolation. Unidirectional, flyback converter, forward converter. In this, I want to give the push-pull converter configuration. Then I don't want to derive all the equations directly. I will do the formula. Okay, that also you remember. Listen. But point to remember, whatever the SMPS circuits we are using, during operation of any SMPS circuit, the basic requirement is it must have regulated power output. The basic requirements of SMPS circuit. Once we are implementing any SMPS, The basic requirements of SMPS converter, switched mode power supply converter is, one is it must have regulated power output. Okay, regulated power output. The power output must be regulated within the specified limits. Like that, we can design the SMPS circuit. It must be isolation transformer. It must have isolation transformer. The purpose of using isolation transformer is to isolate the low power SMPS circuit from the high power circuit. To isolate the low power SMPS circuit from high power supply, we can use the isolation transformer. It must have multiple outputs. Multiple outputs. We can design with multiple outputs. The another basic requirement is it must be less weight. Whatever the SMPS circuit we are designing, that must be less weight. And it must be less cost. It must be designed with less cost. Compact size. That is small size. Compact size. And high efficiency. With these basic requirements only, we can design any SMPS circuit. These are the basic requirements of SMPS circuit. The another point you remember, whatever the transformer we are using, isolation transformer. In normal utility system also we can use isolation transformer. Even in the SMPS also we can use the isolation transformer. Then what is the difference between transformer used in the normal utility system and what is the transformer used in the SMPS? That is the transformer in normal utility system. Transformer in utility system. Then transformer in SMPS. Transformer in SMPS. If you compare these two, that is, the excitation is voltage and current is pure sinusoidal. In this, voltage and currents are sinusoidal. But in the case of SMPS is voltage and current is non-sinusoidal. You don't expect always sinusoidal. This is non-sinusoidal. The transformer is subjected with non-sinusoidal. Then used for 50 to 60 Hz frequency. We can design with 50 to 60 Hz frequency. Used at a kilohertz frequency. It is designed for kilohertz frequency. Then core is made with soft magnetic material. Core is made with soft magnetic material. We can use the soft magnetic material. The example is silicon steel. Silicon steel we can use. Core is made with soft magnetic material. But in the case of transformer is used in SMPS circuit, hard magnetic material. Core is made with hard magnetic material. Hard magnetic material. The example of hard magnetic material is we can use ferrite core. We can use the ferrite core. Then these are used for medium and high power applications. Mainly designed for medium and high power. And these are used for very low power application. Very low power application. This is a selection of transformer in utility system and transformer in SMPS system. Okay, this is some introduction to the SMPS circuit. That is switch mode power supply. Quick no doubt. Flyback converter. Now see it consists of isolation transformer at input side. This is flyback converter. Some switch arrangement. Input is constant DC, VDC. Can use one isolation transformer. Capacitor. Inductor. Capacitor. This converter is nothing but a flyback converter. Resistance positive negative V0. The number of turns in primary is N1, number of turns in secondary is N2. Note down quick. The switch arrangement. With the transformer we are representing. That is, the turns ratio is N1 is to N2. The operation of this circuit is same what I explained in the buck boost converter. It is, listen please, switch is on, diodes are off, apply the KVL, analyze that. Switch is off, diode is on, apply the KVL, analyze that. Then in this case, the V0 equal to, by deriving this one, I am not giving any derivation. The knowledge, the fundamental knowledge is already given. With that knowledge, you try. V0 equal to VDC into D by, or the value of V0, D by 1 minus D into N2 by N1. This is the output voltage for flyback converter. Without this turns ratio, it's just like VDC into D by 1 minus D. Na? VDC into D by 1 minus D, that is which output? Buck boost converter. That's why where D is a duty cycle. Duty cycle. A point to remember, therefore, without isolation, it is a buck boost converter. That's why it is also called isolated buck boost converter. It is also called isolated buck boost converter. With isolation transformer we are using. Isolated buck boost converter. Isolated buck boost. Okay. A flyback converter is also called. That means you remember the buck boost converter formula, multiply with N2 by N1, that gives the V0. Simply remember like that. Okay. Next. Ideal forward converter. Ideal forward converter. Then what is the circuit we are using for ideal forward converter? Okay. Then this is switch arrangement with the transformer primary. The supply voltage is VD. And this is secondary. D1 diode, D2 diode, inductor, capacitor. We are supplying the power to the resistive load, R, positive, negative. This is this picture. This N1 number of turns, this N2 number of turns. The turns ratio is N1. This is the ideal forward converter. Okay. Switch arranged at the transformer side. Here we are using the diode. It's just like diode across the load. Na? Then which converter? Buck converter. In buck converter, what is the formula? DVD. Then here we are using turns ratio. No? Easy to remember. Then what is the average output voltage? V naught equal to dVdC into this is the average output voltage V naught equal to dVdC into N2 by N1. Easy to remember. Let this is a buck converter with transformer, that is into N2 by N1. But it is also called isolated buck converter. It is also called isolated buck converter. Isolated buck converter. Okay, no need of all these derivations also. Just to remember. One more configuration I want to give here. Ideal forward converter, that is a forward converter with a tertiary winding. This I want to see. Forward converter with a tertiary winding. Forward converter with tertiary winding. Now see how to draw that configuration. A forward converter with a tertiary winding. And draw like. And this is a switch arrangement. Remaining as it is. Extra one winding is added. Inductor, capacitor, resistor. This is D3 diode. This is D2 diode. Yes. That you take, this is D1 diode, D2 diode. Voltage across the resistor is this inductor. This is, that this is N1 turns, this is N2 turns, this is N3. That is N3 is to N2 is to N1. The supply voltage is Vd. This winding is tertiary winding. Okay, this is forward converter with tertiary winding. Now for this case, how to write average output voltage? Directly I am giving V0 equal to dVdC by into N2 by N1. Same formula you can get. But here D is nothing but a N1 by N1 plus N3. This is it. No need of derivation directly. Okay, no doubt. Okay, these are the, what is flyback converter, what the output voltage, ideal forward converter, how to write average output voltage, forward converter with a tertiary winding, how to write the output voltage. Okay, no doubt. One more configuration I want to give, that is bidirectional converter, that is bidirectional excitation, that is nothing but a push-pull converter. This is also important for computing. You write what is the configuration of push-pull converter. You draw the configuration of push-pull converter. Okay, this is the configuration of push-pull converter. push-pull converter. Bidirectional excitation. Parallelly draw the circuit. Switch 1, switch 2, VD. Take like this. This is N11, N12, N12, this N21, this N22. Number of turns in the secondary winding, number of turns in the primary winding, like this. First winding, second winding. Secondary, first winding, secondary, second winding. Okay. This D1 diode, this D2 diode. Then inductor, capacitor, supplying the power to the resistor. R, I naught, C, L. This is D1 diode. This is push-pull converter. No doubt. The supply voltage like this. Yes. No doubt. Quick. Here, this circuit operation is explained under the assumption of N11 equal to N12 equal to N1 by 2. Each is N1 by 2. N21 equal to N22 equal to N2 by 2. That means this N2 number of turns means this is 50%, this is 50%, this is 50%, this is 50%. With that assumption only, we are drawing this part. We are writing this part. That this voltage is V01 and this voltage is V0. By analyzing this operation, then we can write V01 equal to dVdC into N2 by N1 we can get. It is similar to that of buck converter. dVdC into N2 by N1 we can get. Next, we can make this switch 2 is on, then we can get V02 equal to dVdC into N2 by N1. Then resultant voltage, the resultant output voltage V0 equal to V01 plus V02. Then what we can get 2 into VDC into D into N2 by N1. This is the output voltage of push-pull converter. If you remember. Okay, this about what exactly SMPS circuits we are using. So this knowledge is enough. With this knowledge, we can answer any question based on the push-pull converter, whatever the questions asked in computation exam. Mainly based on this concept, only one time it is asked in GATE exam, 1 or 2 times only. But these formulas are important to solve the questions in IS objective point of view. In IS exam, there is a syllabus on SMPS, switchable mode power supply. But I'm not giving this concept with respect to descriptive point of view. Okay, if you want descriptive point of view, means we make the derivations only. How to make the derivation means switch is on, switch is off. Like that, we can make the KVL. Then we can apply energy balance theory. Like that, then we can derive the formulas for average output voltage, average load current. We also find what is the peak to peak ripple voltage. All these we can calculate. Ripple currents also we can calculate. But that analysis is not required. That's why I'm giving only some introduction with respect to SMPS. Okay, with this, with respect to chapter 7, types of choppers based on output voltage level, that is buck regulator, boost regulator, buck boost regulator is completed. Types of choppers based on the quadrant operation. Then based on the types of choppers based on the output voltage level, I solved already classroom workbook questions. Then types of choppers based on the quadrant operation, type A chopper, type B chopper, type C chopper, type D chopper, type E chopper, in detail that I already explained. Then I given some differences also with respect to quadrant operation, with respect to application also I given with respect to types of choppers based on quadrant operation, and steady state analysis of type A chopper also I explained. Then based on that steady state analysis of type A chopper and types of choppers based on the quadrant operation, I solved already some problems. That classroom workbook questions is also completed. Then I started what is the tank circuit, that is the concept of LC circuit is I explained. In the concept of LC circuit, it's different conditions I explained without any initial conditions in the capacitor and the inductor, with initial conditions in the capacitor and inductor, that formulas also I given, in detail that I given. And I started types of choppers based on the commutation. I discussed about the load commutation, then class D commutation, that is voltage commutated chopper that I discussed. Class B commutation that I discussed current commutated chopper. Then that I given what is the load commutated chopper. Brief discussion I given for Jones chopper and Morgan chopper. Then I discussed about AC chopper. Then after that I discussed about multi-phase choppers also I discussed. Then how to analyze how to write the formula in multi-phase choppers also I given. Then after that I explained about class C commutation and class C commutation. That is complementary commutation with waveforms I discussed and derivation also I discussed. That you concentrate. Then after that I discussed about class C commutation and class C commutation. External pulse commutation also I explained. Then this is push-pull converter. How to write the formulas in, how to write in SMPS different types of converters, that is flyback converter, forward converter, and push-pull converter. How to write the formulas also that I discussed. So this in detail about chopper. Now based on this, I solve the problems based on types of chopper based on output voltage level, types of choppers based on the quadrant operation. Then we will solve the types of choppers based on the commutation. One or two problems on multi-phase choppers, and based on the commutation method also we want to solve the problems. Then based on SMPS, one or two problems also we want. Then in the next session, next 1 or 2 sessions, I will discuss the classroom workbook problems. With that, choppers will be complete. The concept of choppers will be, that is chapter 7 will be complete. Okay, thanks. The next session will continue with classroom work. Okay, on the choppers.